Welcome to Zero Knowledge. I'm your host, Anna Rose. In this podcast, we will be exploring the latest in zero-knowledge research and the decentralized web, as well as new paradigms that promise to change the way we interact and transact online. Hey, so I'm still technically on break from the show, but as I mentioned in my last weekly episode, I do have the plan to release 1 or 2 episodes this fall. Well, this is one of them. This week, I catch up with Dan Boneh for an update on the ZK research problems and ZK themes he and his students at Stanford are working on. The last time he was on was over 2 years ago, so it felt like a great time to bring him back on the show. We had a lot to discuss. We covered lattice-based SNARKs, ZK in the FHE context, extensions on the content provenance work he presented last time he was on the show, updates on ZKML, we talked about folding, co-SNARKs, and much, much more. Now, before we kick off this episode, I wanted to highlight for you the ZK Jobs Board. There you can find job offerings from top teams working in ZK. There are always new jobs being posted, so check out the link in the show notes and find your next job working in our space. I also want to let you know about ZK Hack Online 5 that just kicked off this week. ZK Hack Online is different from the hackathons we've hosted this past year. First, as the name suggests, ZK Hack Online is an event that is completely virtual. And second, it isn't a hackathon. It's a format that we pioneered back in 2021, and we've been running ever since. It consists of a 4-week workshop series with a CTF-like puzzle hacking competition running in parallel. We also are hosting a virtual ZK Jobs Fair to wrap up our event after the final workshop. This is our 5th edition, and the event will be running until December 17th. So come join us and get to know the ZK Hack community. To learn more, head over to the website over at zkhack.dev, join our Discord, and jump in. All links can be found in the show notes. Now, Tanya will share a little bit about this week's sponsor.
Today's episode is sponsored by Aleo. A new era of decentralized, privacy-preserving computing is here. Aleo, a Layer 1 blockchain powered by zero-knowledge cryptography, recently announced their mainnet launch. Now developers can build applications that take advantage of Aleo's unique combination of permissionlessness, programmability, and privacy. Start by learning their domain-specific programming language, Leo. Write and deploy your first ZK application at leo-lang.org, or head on over to aleo.org to learn more about their technology and what you can build. Aleo, this is zero knowledge without compromises. So thanks again, Aleo. And now, here's our episode.
Today, I'm here with Dan Boneh. Hi, Dan. Welcome back to the show.
Hey, Anna. Great to be here.
Nice. So last time you were here on the show was actually November 2022. It's been a solid 2 years since you've been on the show. And in that episode, we covered what you were working on at the time, which was very exciting ZK research topics, both on the cryptographic side, but also on the application front. I'm going to add a link to that episode in the show notes. I don't know if I ever told you this, but it's actually one of our most popular episodes, and it's been cited by a lot of our listeners as one of their favorites. So yeah, it's really great to have you back on to continue that conversation and to check in.
Wow, very cool.
I will say this too, like some of the work that you mentioned in that episode also still stands out very much to me. Like we talked about, I think it was the first time I was introduced to this idea of like using ZK in image provenance to show that like a finished picture that's been transformed comes from an original image. And I believe it was the first time, at least on the show, that we talked about collaborative SNARKs, which also has become quite relevant today. I did an episode about 2 months ago with the Tetseo team who are focused just on collaborative SNARKs. So that's also cool that, now there's teams working on it.
Yeah, it's become a big topic. And actually, we're going to discuss collaborative SNARKs later on in the episode.
Cool. So yeah, maybe to kick off, what's new with you in the last 2 years? What kind of research have you gotten excited about? What are you working on?
There's a lot going on in the space. I have to tell you, the space is so much fun to work in. There's just so much activity all the time. I actually looked just before the show today. I looked in 2024. I was just curious how many papers were published on folding, just, kind of a sliver of the SNARK space, just on folding schemes. And I found like 17 papers on ePrint just in 2024. It's a lot of papers and a lot of wonderful, beautiful ideas that come out. So there's a ton happening in the space. I guess in recent months, there's been a lot of work on new code-based SNARKs, new multilinear commitment schemes. The whole field is transitioning to relying much more on sum checks than traditional things we've done before. So there's kind of also a bit of a transition in the space. And so, there's like new folding schemes coming up all the time. Maybe we'll talk about some of those later on in the show, things like Arc and Nebula and others. And so, there's just so much activity, even in the code-based SNARKs, things like Basefold and Blaze and all the other schemes that are coming up. So maybe we'll get to discuss some of those later in the show. But actually, I wanted to start with something very specific. I wanted to start with actually the question of how do we build SNARKs from lattices?
Actually, before we even do that, why would you build SNARKs out of lattices? Like, why would you start to explore that space in the first place?
Yeah, that's a great question. Okay, so first of all, I guess there's sort of 4 types of assumptions that are used to build SNARKs. Yeah, or maybe more generally, 4 types of assumptions that are used to build polynomial commitment schemes. So we have SNARKs and polynomial commitment schemes from pairings. We have them from discrete log. So I guess from pairings, we have KCG and their variants. From discrete log, we have bulletproofs and its variants. From hash-based schemes, we have FRI and many, many other types of hash-based schemes. And then the 4th category is lattices. Yeah, and from and lattices, we also have, it turns out, SNARKs and polynomial commitment schemes that one can use. So there's these 4 families. Pairings, discrete log, hash-based, and lattices. And so you ask why lattices? Well, the first answer that comes to mind is, well, lattices are believed to be post-quantum secure. Okay. So if we build something from lattices, maybe we'll make them, we'll get a SNARK that's post-quantum secure. Of course, the hash-based SNARKs are also post-quantum secure. So of the 4 that I mentioned, pairings and discrete log, of course, are not, but hash-based and lattices are believed to be post-quantum secure. But it turns out there's another reason to try to build things from lattices, and potentially we might actually get better performance. Yeah, and we'll talk about that in just a second.
Do you also need, like, the lattice-based SNARKs? I think when I've heard them referred to, it's actually been in the context of these FHE combo SNARKs, where like they want to use FHE, and that's a different kind of math. And if you had strong lattice-based SNARKs, you could use them better with like the FHE models.
Ooh, yes,
is that
amazing.
true?
Amazing. That's an amazing question, Anna. That's exactly kind of where we're going.
Okay.
But we'll get there in just a second. So we'll see. So first of all, I'm glad you brought up FHE, so fully homomorphic encryption. It's kind of one of the magical powers of lattices, that we can build encryption schemes that support arbitrary computations. If I had to summarize why lattices lead to FHE schemes, the one sentence summary is that lattice encryption systems have a very fast decryption algorithm. And it turns out if you have very fast decryption, you can do something called bootstrapping, and that actually basically leads down to the path of fully homomorphic encryption. Yeah. So if we had other ways to build encryption systems with super fast decryption algorithms, we might have other ways to build FHE. Yeah, so the dream, of course, is always to come up with faster and faster ways to build FHE. Actually, I should probably say that one more time, because it's kind of an important point, that it's not clear that the way we currently build FHE systems is the only way to build FHE systems. There could be a completely different path that we haven't discovered yet that might lead to much more efficient and scalable FHE systems. So this is kind of a challenge to the whole audience, it's great to try to think of other ways to do it. But let's come back to lattices to SNARKs from lattices. Mm-hmm. So let's see. So there are a couple of systems that have been proposed over the last year or two. I guess one that's gotten a lot of attention is a system called Labrador. So Labrador, maybe one way to think about it is it's sort of adapting the bulletproof type work to the lattice space. And the reason I say it is because it's also kind of a folding-like mechanism. And in fact, in Labrador, the basic Labrador, the verifier runs in linear time in the size of the statement, sort of like as it does in bulletproofs.
Okay.
Yeah, so it's a kind of a succinct proof, a short proof, I should say. But the verifier is not very fast. It runs in linear time. as opposed to logarithmic time, or log squared, which is what we would like. So one paper that came out recently is called Greyhound, which actually tries to build a polynomial commitment scheme from lattices. And what they do is they kind of take a two-step approach. They reduce the verifier time to root n using, kind of a technique that's been used before. And once they have now a PCS scheme, a polynomial commitment scheme that takes the verifier root n time to verify, then they apply Labrador to get a short proof. What's interesting is they kind of get, they're able to then do commitments to fairly large polynomials. So for example, maybe just it's worthwhile just saying the numbers, like if you want to commit to a huge degree polynomial, a degree 2 to the 30, so it's a billion degree polynomial, they get a proof that the evaluation proofs are about 53 kilobytes. So not terribly short, but also it's not that long for such a high degree polynomial. And verification time is about 2 seconds. Yeah. So again, not terribly fast, but 2 seconds, I guess, is reasonable. What's interesting is if we compare it to like hash-based SNARKs, let's say the FRI-based mechanisms, for polynomials of degree, say 2 to the 26, these are kind of polynomials that people use FRI to commit to. The verifier is still about 10 times slower. So the lattice verifier is slower than the FRI verifier. It's better in other measures, but the verifier is a little slower.
And this is all Greyhound still.
This is Greyhound. Yeah.
Okay.
So it's a very interesting commitment scheme from lattices. And so the fact that the verifier is still somewhat slow makes this a little bit difficult to use in recursive schemes where you do have to run the verifier inside of the circuit. And so there's definitely more work to do there. So the reason I bring it up is this is kind of an area where there could be a potential for a lot more innovation. So this is something that's maybe people would be interested in looking at. Cool. But why am I talking about lattice-based SNARK? So in some sense, they haven't been adopted into the SNARK world directly, but because when you try to build sort of a monolithic SNARK from lattices, it's not as maybe as great as what you would get from other schemes. But it turns out, surprisingly, lattices are great for folding schemes. Oh. Yeah, and that's kind of what we started looking at. This is the scheme called the lattice fold. This is joint work with Boneh Chen. Boneh is amazing, by the way. He's also applying for academic positions. So if you know of an available academic position, you should jump all over him because Boneh is really quite a creative and amazing researcher in this area.
Is this Boneh from Espresso?
Well, this is Boneh, who formerly from Espresso and currently my postdoc. Indeed.
Oh, okay. Got it. Nice.
Indeed. But he's done a lot of work in the space. Maybe you remember Protostar and
yes.
And
exactly.
Lattice Fold and many other.
I think we
other
had him on
well.
the show actually. I'm pretty sure he's been on the Zero Knowledge podcast. So I'll find that episode too. And
he's also a co-author on Basefold and Blaze and lots of kind of exciting developments in the space. So let me talk a little bit about lattice fold. So in when you do folding, like in Nova and Hypernova, I'm sure you've talked about Nova and Hypernova and variants on the show. What happens is basically those schemes rely on what we call a homomorphic commitment scheme, right? Where I can commit to some message M, I can commit to some message M prime, and then I can add the commitments and get a commitment to M plus M prime. Yeah, these are called linearly homomorphic commitments. And typically, the homomorphic commitments that people use is what's called a Pedersen commitment. Yeah, so Pedersen commitments are based on multiscalar multiplications. And so that's what these schemes typically use. But it turns out we have another linearly homomorphic commitment scheme. And this one comes from lattices. Yeah, and the scheme is actually kind of a classic commitment scheme. It's called the ITI commitment scheme, based on the ITI hash. So the ITI hash in its simplest form is simply a matrix vector product where the matrix is wide and short. Yeah, so it's a very wide matrix that doesn't have that many rows in it. And so you can see if you multiply the matrix by a vector, what happens is you take a very long vector and the output of the matrix vector product is a very short vector. Yeah, so it's compressing. This is why it's actually a collision resistant hash. And then you can use it as a commitment scheme. And because it's a matrix vector product, it's additively homomorphic. Okay, so that's the ITI hash. It's a very simple hash to describe.
Where does that come from? Like, when was that invented, and where? Like, is it from a different part of math and now has been brought in? Or, where is that from?
Yeah. Well, it was invented by Aitai back in the late 90s.
Okay.
Yeah, and it was invented for, in a completely different context for a completely different reason, actually.
I love it when that happens. That's so cool.
Yes, indeed. So in fact, the SNARK space borrows from a lot of different areas of mathematics, from pairings, discrete log, elliptic curves, and of course hash functions and codes, and maybe now some lattices too. So we have this very simple hash. It's just a matrix vector product. Because of that, it's linearly homomorphic. And so the question is, could we use it for a folding scheme? Yeah. So we have a way to commit in such a way that is additively homomorphic. So potentially we can use that to fold. The problem is that the Aitai hash is a little difficult to use. Yeah, it sounds great. Yeah, we have a commitment scheme. It's fast, but it's a little difficult to use. Why is it difficult to use? It turns out it's only collision resistant when the inputs to it are low norm. Yeah, so the vectors that you hash, they have to be short vectors.
Okay.
If you allow for arbitrary length vectors, it's trivially not collision resistant. Yeah, that's easy to see. But if you restrict the inputs to be short vectors that have a low L2 norm, they're short, then it turns out it's actually collision resistant. In other words, it's hard to find two short vectors that will map to the same output. Okay, and from that you can build a commitment scheme, and as we said, it's additively homomorphic. So great, so we can throw this into folding, right? So folding, as we said, is basically based on adding commitments, and to verify, all it does is it just verifies that commitments were added correctly. So we can throw that into folding, and you can say we're done. Yeah, but that doesn't work.
Okay, but why wouldn't it work then?
Yeah, so it's a great question. And in fact, it turns out that when we fold, what we do is we multiply one vector by a scalar, and we add it by a random scalar, and we add it to the other vector. And so folding sort of inherently makes the vectors be large. It increases the norm of the vectors. Yeah, because folding inherently means you take a random linear combination of things, and taking random linear combination causes things to grow in norm. Yeah, if you multiply a short vector by a constant, you get a much bigger vector. Yeah, and as a result, you can't just use the Aitai hash directly for folding. Yeah, so that's kind of, it doesn't just work.
Okay.
So we need to solve this somehow.
You have to do something to it, or transform it, or
Exactly. So you have to do some sort of a norm reduction process. Yeah, exactly. You can't just do folding on these committed vectors, because pretty soon they will go out of the interval where the hash function is committing, and then things will no longer be secure. So what we do is basically we apply a norm reduction step. Yeah, and this is kind of, again, very common in the FHE world. We borrow a technique from the FHE world where we do this step called decomposition, where the way you reduce the norm of something is you decompose it into smaller things. You represent it as a sum of smaller things. And so what you do is you want to fold two instances. Each one of the instances you decompose into multiple instances. And now you fold all those instances together, and you end up with one instance that's guaranteed to still be low norm.
Okay.
Yeah, so that's kind of the basic folding mechanism. That's kind of problem one. But problem two, we're not done yet, because in problem two is that the prover has to prove to you that the initial commitment that they gave to you, in fact, is a commitment to a short vector. Yeah. So in addition, there's a process in lattice fold where the prover provides a range proof to prove that the commitments are commitments to short values, and you kind of put these things together, and you can actually get a folding scheme from the Aitai hash. Yeah. So I'm oversimplifying, of course. There's a lot of steps involved, but effectively you get a very efficient folding scheme from the Aitai hash. Yeah. So our motivation originally was just to get a post-quantum lattice-based folding scheme. Surprisingly, though, but just because the Aitai hash turns out to be so fast, this actually could be a competitive folding scheme. So not only do we get something that's post-quantum, it has a potential for being even performant. So there's actually a company that's implementing this now. So hopefully, I was hoping that by the time we do this podcast, I'll have running time numbers for you. But everything takes longer than you expect. And so hopefully we'll know soon how well this actually works in practice.
I have a question. So the first change you had to make, like the norm reduction step, does that add a layer to this construction? Like or multiple layers? And does that slow it down? Like, does that sort of cut into what makes it so fast?
Yeah, it does actually. So you now all of a sudden, instead of just folding two things, you decompose and now you fold multiple things. And in addition, you have to do a range check. Yeah. So if it was just as simple as replacing Pedersen hash with an ITI hash, everything would be 30 times faster.
Okay.
But that's not that simple. You have to do a few more steps, and that actually slows things down, of course. And the question is, do we lose more than we gain, or do we gain more than we lose?
Yeah.
And that's the sort of thing that we'll only discover from an implementation. So hopefully, we'll have numbers soon. Now, I should say we're actually working also on an improvement to this. So, the story never ends with SNARKs. There's always ways to optimize and improve. So, stay tuned. There are improvements to Lattice-fold that are coming. So that's all kind of nice and fun.
Nice.
But then something really interesting happened. So it turns out, because we can now do folding schemes using lattices, it turns out that the rings that Lattice-fold uses are exactly the same rings that are used in fully homomorphic encryption.
Whoa.
Yeah. So that was kind of that was a bit of an unexpected.
Was that a surprise, or did you design towards that? Like, was that actually an accident, or?
Yeah, I guess when you use lattices, it's kind of a natural thing to use those rings, and It turns out those rings are also useful in FHE.
I see.
Yeah, maybe I can claim it's an accident, but really it's it's one of those things where you can only go one way, so you end up doing the same things that are also done in FHE.
Is it because they're borrowing from the same initial, like it's kind of coming from the same math?
Yeah, same underlying math, so you kind of end up with similar algebraic structures. Yeah, so it's not too surprising, I suppose. But the cool thing about that is that there's as you might know, there's actually a lot of work in the FHE space now to build custom ASICs to speed up FHE. Mm-hmm. So this is like, everybody's waiting for this. Supposedly this coming year in 2025, we're going to start seeing ASICs that speed up FHE.
Wow.
And the claim is that, maybe that will speed up FHE by who knows, a factor of 10, a factor of 100. People throw out all sorts of factors, but until we see the actual ASICs, we won't actually know. So what that means is really, surprise, Lattice-fold can actually benefit automatically from the ASICs that are being developed in the FHE world, which is kind of interesting. But it turns out that brings up a connection between FHE and lattice-based SNARKs that I wanted to highlight. So one of the issues with FHE, in some sense you could say it's a limitation of FHE, is if I ask you to compute on encrypted data that I give to you, mm-hmm. The question is, how do I know that you did the computation correctly, right? Maybe you claim that you did a certain computation on the encrypted data, but maybe you did a different computation, and what you send me back is just garbage.
I see.
That when I decrypt, I'll get garbage, right?
But so it's not that they can see it. It's not that, because it's encrypted. So it is, the privacy is kept intact, but it's more that the action that's being done on it could be false or...
So it's not a confidentiality problem, it's an integrity problem. How do we know that the server computed what I asked it to compute on the encrypted data? Yeah, in some sense, this is always brought up as a limitation of FHE. There are situations where it doesn't really matter, but in some cases, you would like to basically have integrity on top of the confidentiality. So what do? How do we get integrity? Gee, if we only had an integrity providing tool, and that's exactly a SNARK.
Totally.
Yeah? So the FHE world is kind of interested in providing integrity by actually running a SNARK on top of the FHE. Yeah. So what will come back is when you send encrypted data to the server to compute on, the server will do the computation and send you back the encrypted data along with a proof that it did the right computation. Yeah.
This sounds a bit like just this idea of the untrusted server and needing to interact with it. It makes me think a little bit of the co-SNARK world, even though I realize the co-SNARK is its goal is to keep that privacy. If you send the information you want proved to an untrusted server, the privacy is revealed. And that's kind of the challenge that co-SNARKs are trying to take care of. Here, you're using a SNARK to prove that untrusted server is acting right.
Exactly. And actually, we'll get to the co-SNARKs actually in just a second. It's a very, very good connection, Anna. Very prescient. Right. So yes. So SNARKs can be used basically to prove that FHE was carried out correctly. And so there's kind of interest in, for example, in Zama, in implementing SNARKs on top of FHE. Yeah. So you run the FHE and then you run the SNARK on the FHE computation itself. And so folding schemes come to mind, and in fact, folding schemes that are friendly to FHE would make a lot of sense. And in some sense, Latticeful, because it uses the same rings as FHE, the two kind of play nicely together. So this is something that people in the FHE world are looking at. And then this is kind of I wanted to jump to the other way, the other direction, which is kind of where co-SNARKs come in. So far we talked about how SNARKs can be used to authenticate FHE computation. It turns out that FHEs can also help the SNARK world. So how can they help the SNARK world? Well, this is where kind of co-SNARKs come in. So in a collaborative SNARK, maybe the secret witness that we're trying to compute a proof over is shared across multiple parties. Yeah, maybe naturally the data is already shared across multiple parties, and together they're trying to produce a proof that something is true. Yeah, this comes up, you can imagine, a lot in the banking world, where maybe multiple banks share that, like they each have a view of the transaction graph in the world, and they're trying to prove a global statement about the transaction graph. So together they're trying to produce a SNARK that something is true, but they're not allowed to share to send the data to each other. So they need to collaborate in order to produce the SNARK. Yeah, so there's a long line of work on collaborative SNARKs. I guess this was started by Alex Ozdemir and me, and followed up by a number of works as well. And basically, how do we get collaborative SNARKs to work? And we do that using basically MPC. So we use multi-party computation to speed up the SNARK generation process. And it turns out this is kind of an unusual situation where MPC doesn't add a lot of overhead. Yeah, because most of the SNARK generation work can be done locally, even if the data is shared. It's very unusual, but this is a situation where MPC is quite efficient. It doesn't add much overhead above the SNARK generation. In fact, Sanjam Garg actually has some work that shows that not only does MPC not harm SNARK generation, it can actually speed up SNARK generation, because now you have multiple machines that you can potentially use to generate the SNARK. Yeah. So that's pretty interesting. But where does FHE come in?
Is FHE replacing the MPC in this construction?
Yeah, you got it. Exactly. So one thing you might try to do is say, well, maybe each one of the parties that holds a share of the witness, maybe what they can do is they can encrypt their witness under an FHE, send it to a central server. And now let's think about, what is the central server doing? So now the central server has a bunch of FHE encryptions of the witness, and it wants to generate a SNARK on top of the witness. So now what it's going to be doing is it's going to be running the SNARK prover on encrypted data, on the encrypted witness.
How does a verifier, though, in the end state ever verify back to, like, it can't verify what was in the encrypted data? It has to trust the FHE.
No, not quite. So what will happen is, maybe we should use a simpler example. One way to describe this is we have a witness that's shared across multiple parties, and we use FHE basically to compute on the encrypted witness to compute an encrypted SNARK. But now once we have an encrypted SNARK, that's not useful for anybody, because it's encrypted. So then what will happen is the parties that actually ask for the SNARK to be generated will do a threshold decryption of the encrypted SNARK, and they'll get the SNARK in the clear.
I think I followed, like, you've encrypted it using FHE, and then you've sent it over to a SNARK, and it's making a proof of that encrypted data and like the final thing is a proof that could be verified. But to me, a verification of that only goes back one step, right? It only goes back to the prover of the encrypted data. It doesn't go all the way back to the clear data.
Okay. So let's actually explain it using maybe a simpler setup. Yeah. So I jumped 2 steps.
Okay.
So let's say we have a simpler setup. Let's suppose, Anna, you have a witness, and you're trying to generate a SNARK. That witness satisfies a certain property. Okay. And let's suppose that you're like a weak device, like maybe you're like a cell phone, or maybe you're running inside of a WASM virtual machine. You don't have a lot of memory. You don't have a lot of time.
Okay.
What you could do is you could generate the entire SNARK locally. Yeah, but that might take some effort. That might take a lot of memory on your part. Instead, what you could do is you could take your witness, FHE encrypt it, and send it to a remote server. Yeah. Now the remote server could run the entire SNARK prover on the encrypted witness. Yeah, and what the remote server will get from that is an encrypted SNARK, an encrypted proof. Yeah, it will send the encrypted proof back to you, and now you can decrypt it and get the proof in the clear.
The whole goal of this is the sort of being able to use the untrusted server to do the proof generation.
Exactly.
I get it. Okay, because I think I was confused as to like the goal of this, but the goal is just to be able to use that computation power.
Yeah, actually there are multiple goals here, so we can let's go over them one by one. So if you're like a weak device and you're trying to create a SNARK, you could generate the SNARK yourself, but then you have to do the entire SNARK processing. You have to run the entire prover yourself.
Okay.
Alternatively, you can encrypt your witness under FHE, send it to the server. The server will run the prover under the FHE, send you back the encrypted proof, and you'll decrypt it. So now all you're doing, you, the client, all you're doing is you're just encrypting and decrypting. Yeah, so now supposedly you're doing much less work. This is, of course, a lot harder for the server. The poor server has to run the entire SNARK prover under FHE.
Right.
And that's actually where the interesting research problem starts.
Okay.
Yeah, so maybe just to take this back one step and connect it to collaborative SNARKs. In the world of collaborative SNARKs, what happened is the witness is distributed across multiple servers, and they don't collude. The servers don't collude with one another, and they run an NPC to generate a SNARK. Here, effectively, they could all outsource SNARK generation to a single server. So you don't need this non-collusion assumption. You have a single server that generates a SNARK, but now the single server has to do much more work because it's doing proof generation under an FHE.
But are we imagining this untrusted server also could be like an incredible machine with the ASICs? Like you could beef that up so it could handle it?
Potentially, yeah, okay. Exactly. Potentially, yeah, that would clearly have to be a very powerful machine. What's interesting is there has actually been there have been 2 papers on this idea now. Unfortunately, these papers don't have system names to it, so I can't quite refer to them by the system names where people can just look it up. Okay. But there are 2 papers on ePrint that actually talk about using FHE for computing SNARKs. I'll say one is from Sanjam Gar's group, and one is from Verkadaran's group. What's interesting is they use, for example, I'll mention the latest paper. They use, as the SNARK system, they use Fractal. And as the FHE system, they use what's called a generalized BFV FHE. Yeah. And I'll just say the claim in the paper is that for 1 million constraints, yeah, so not too big, but 1 million constraints is still 1 million constraints. The server can do this in about 20 minutes. Yeah, okay. So the server can generate a SNARK proof on an encrypted witness in about 20 minutes. And then the cool thing is the client doesn't need to do, the client is just encrypting and decrypting. That's it. So I'm not saying this is something you should run out tomorrow and implement, because this is still, fairly theoretical, fairly long-term. But what's interesting here is maybe there's an opportunity to design FHE systems that are especially compatible with SNARKs, with SNARK provers, so that the FHE computation on top of the SNARK is not as expensive as it could be. So yeah, I just wanted to mention it as kind of a interesting direction for future work. Potentially, that might make it easier to generate SNARK proofs on clients where the client now just has to do encryption, decryption, rather than just running the entire proof generation process.
Is the prover on this untrusted server that's creating a proof in FHE somewhat, is it actually using any of the lattice-based stuff you talked about before? Or are these very distinct works?
Oh, no. That's exactly right. Yeah. Okay. So the FHE right now is all about lattices. Yeah. Okay. So presumably the SNARK that we would like to use would also involve similar algebraic structures, although the work that's been done, so the 2 papers that I mentioned so far to do this don't actually use lattices. They're more in the, interestingly, they're more in the hash-based SNARK world.
Would it be helpful to be lattice? Because then if you did create the better hardware, you could take advantage of that, for both? Because you'd be basically optimizing the hardware for lattice-based everything.
Potentially, yeah. So again, I don't want to get people overly excited about this, because this is still very far away. Yeah, it's not clear exactly when this will be useful, how this will work. Is it really better than computing the SNARK locally? But I guess in a situation where the witness is naturally distributed across multiple parties, you could think about using a collaborative SNARK to do proof generation, or you can think about using a collaborative SNARK using FHE, where they all outsource the computation to a single server. the single server generates the encrypted SNARK, and then the participants jointly decrypt using a threshold decryption. Yeah, so this is just potential architecture. So the future, don't run out and immediately implement these things. These are right now, these are still just research directions.
So last year, I feel like I had many conversations about folding, but at the time, it was like folding only worked in the pairing-based kind of world. And I heard that some of the folding work was starting to transition into the hash-based, that people were experimenting. But here you almost see like folding breaking out even from there, that like you're starting to see it combined with lattice and the things that opens up. Like it's a technique that, yeah, I sort of felt had been relegated to one quadrant, and now we're seeing it being used everywhere.
Oh, folding is going to take over the world. I mean,
Wow.
Folding is a really, really important technique that, it basically allows you to break a very large proof into many small proofs.
Yeah.
And kind of do them all these pieces, do them all at the same time. Actually, it's interesting that you mention folding in the hash-based world, because there I want to mention there's been kind of a pretty interesting development. There's a paper called ARC, ARC, just recently posted on ePrint. It's by Benedict, Pratouche, Wilson, and William. And that actually allows you to do folding without homomorphic commitments. Yeah, remember how we talked about folding required homomorphic commitments?
Yeah.
So you either use Pedersen hashes or ITI hashes. And ARC basically allows you to do folding even though you have a commitment scheme that's not homomorphic. Specifically, it's for hash-based, what's called hash-based accumulation. Yeah, so for hash-based schemes, these will also be post-quantum, and they're compatible with much of what's being implemented today. And so ARC, I think, that's a pretty important step in the world of folding, because it does allow folding to also happen on these hash-based schemes. And so, for example, if you need to do proofs client-side on a low-memory machine, folding is almost the only option available to you. And potentially using ARC, you could actually do that using a hash-based scheme rather than a additively homomorphic commitment. Yeah, so it's good to keep in mind. ARC is a pretty interesting paper, I think.
All right, I think we've covered a lot of ground on the folding and the FHE.
Yes.
But what else, Dan? I know there's multiple research threads that you're always kind of exploring at the same time. So what's next? Yeah,
so let's pop up a level. I guess maybe we started a little technical, so maybe we can pop up and talk about more applications of SNARKs. Cool. So there are actually two applications I wanted to talk about. So one is I wanted to revisit actually the work on using zero knowledge to fight disinformation, and particularly to prove image manipulations.
Yes.
But maybe before we do that, I'll very, very briefly talk about some recent work that we did on ZK in the machine learning world.
Oh, yeah? Cool.
And so the traditional ZKML question is the following, right? I have some data and you have a model. I want to send you my data and I want you to evaluate your model on my data and send the result back to me. But in ZKML, you also send me a proof that you evaluated the model correctly.
Yes.
Yeah, you didn't take a shortcut or so on. So the point of ZKML is you have a committed model, and now I have some guarantees that you evaluated the committed model correctly on the data that I sent you.
Yes. It's a bit similar to what you described before, where it's like something's happening in the FHE context. You want to prove that it's being run correctly. And here, in this case, it's the ML model, the sort of black box that they're using. You want to prove that they're doing what they're saying they're doing.
Exactly. They have a committed model, and they want to prove that they evaluated the model correctly with respect to the commitment. There are a bunch of libraries that actually do ZKML, ZK proofs for ML in a reasonable amount of time. What we were interested in is the following question: suppose you use a machine learning model to decide some critical things, like to decide who gets a mortgage or not. Yeah, so you send your financial data to the bank. The bank runs a machine learning model and decides whether you get a loan or you get a mortgage or whatever. Yeah, based on the financial data. One thing that people worry about in this context is fairness. Yeah, how do we know that the same model was run for everybody? Like, maybe the bank ran one model for you and one model for me, and now we're treated differently. Yeah, so that is something that ZKML actually helps with, because the bank can prove that all the results are always done using the same committed model, right? That's what ZKML does. It's the same committed model that's applied to everybody's data. But that's not enough. How do we know that this model actually is fair?
So they might have run the same model, but maybe there's something in that model that, I guess, are you looking for bias?
Yeah, exactly. So here we're kind of borrowing a notion from a whole area called algorithmic fairness. So algorithmic fairness is a huge area of research. Basically, how do we test that machine learning models are actually fair? In particular, the notion we're using is called what's called individual fairness, which says that similar people should be treated similarly. Okay. So what you'd like to say is basically, the bank didn't make its decision based on your gender only, or didn't make its decision based on your zip code only. Yeah. The bank is kind of fair. Yeah. So if you and I are similar, the model treats both of us in a similar way. Well, so guess what? So we have a system called FairProof that what it does is when you submit a query to the model, you submit your financial data to the model comes back with a proof saying, yes, I used a common model to evaluate your query, but I also prove to you that for your data, the model is fair. In other words, it would have given you the same decision even if you changed like your gender or your zip code or other sort of protected characteristics.
Is it to get that proof, though, do you have to run it again? Like, do you have to kind of run it with variations and then prove that the outcome was the same?
So what you need to do is you need to look at the geometry of the model. And so you look at the data points that I send you. You look at a box around this data point and you prove that in this entire box, the model would have made the same decisions everywhere. So it's not just a matter of querying a couple of other points. It's proving that in the entire box, all the decisions are the same. Yeah. So we call this fair proof. Yeah. It works actually quite well. It doesn't work for ChatGPT style models, but it does work for relatively simple models like what are used for financial decisions.
Interesting.
And so, this is kind of opening up kind of a new direction for ZKML in that you don't just prove that the model was evaluated correctly, but you also prove certain properties of the evaluation, like fairness. So one thing you might want to do is kind of prove like a universal fairness of the model, right? That the model is fair for all possible inputs. But that usually we can't do. Yeah, these models are so complicated that we can't kind of give a universal proof that the model is fair everywhere.
Okay.
What we can do is given a particular query, we can say, for this query, the model is fair. Yeah, so that's why the proofs have to be done sort of online. For every query, we have to generate a proof that for this query, the model was A, evaluated correctly, and B, the response is fair. Yeah, in the notion that we defined.
In this model, is there something that the ML side of things, the ML researchers were already doing to do this kind of verification that we're borrowing? Or was this all the whole construction is coming out of your lab, that they were not checking this and now we need to check it for the first time?
Absolutely. So this notion actually is very closely related to what's called the notion of robustness for machine learning, where you want to argue that small changes don't change the results. This is what's known as robustness. What's new is the ZK part of it. Yeah. So robustness is something that was sort of checked offline and not shared with anybody. And now we can actually, using ZK, we can send it back to the client and say, look, there's a proof here that the model treated you correctly.
I see. Had it been human auditors doing that check?
Well, actually, right now it's not done. But what's interesting here is I just want kind of the listeners to think more about there are many applications of ZK to ML that maybe we haven't explored. And for example, proof of fairness is one thing that there is to add. Yeah, there's probably other things. In fact, we're working on other things that we can prove about a model. And so maybe the next time I come, I can talk about that.
Sounds good.
So there's definitely interesting connections between ZK and ML, basically proving that models are used adequately. Yeah, that space I think will continue to evolve. So that's on the ZK on the ML side. I wanted to go back to images because that's, I think, as you said, as you can see, that's also something that I'm very excited about.
Yep.
So maybe it's worthwhile just recapping how ZK is used for proving image manipulation.
Or image provenance too. Yeah. Showing where it comes from.
Yeah, exactly. So let's just do a quick reminder for folks. So there's a standard called C2PA, stands for Content, Provenance, and Authenticity, where cameras have secret keys embedded in them. Every time you take a picture of a scene, basically the camera will sign the scene. And then as a result, the viewer who looks at the image can tell, oh, this image came from that camera and it was taken at this time using, this location potentially, and the camera was in this and that configuration when it took the image. And so it gives you sort of provenance that this is an image from a real camera. And by the way, what's a new thing that's happened since we last talked is that even the Gen AI models now will issue a C2PA attestation. Yeah, so for example, DALL-E, when you ask it to generate an image for you, the image will come with a C2PA attestation, which is pretty interesting.
And is it saying this is generated by AI? That's it's actually saying, okay. And because I think when we spoke about it last time, we were talking about image provenance more like as a defensive measure against AI, like that you could prove that, a photo had been taken by a certain device by a person by using this kind of ZKPs through every transition, every transformation. In this case, the AI itself is also saying no, this is AI. And so then if you were to transform that using ZKPs, you'd also be able to prove that it's AI.
Exactly. That's exactly right. Yeah. So it's image provenance, whether you tie it back to a real camera or whether you tie it back to a Gen AI model.
Cool.
You'll know where the image came from. That's the point. So I think that the hope is that maybe in 10 years, every piece of content will have some sort of a provenance attestation attached to it. And content that doesn't have provenance attestation to it basically will be dropped on the floor. Yeah, so eventually I think everybody will, because you just can't trust it. You don't know where it came from. Yeah, so it sounds like everybody will eventually race to generate these provenance attestations, and that's how we'll deal with having some trust in the content that we're consuming. Yeah, we'll know where it came from.
And you're predicting 10 years. I think I have a sense that we'll for sure see these things before the 10-year mark. But I think what you're hinting is that in 10 years, it's almost everything will need to have it.
Well, okay, 10 years is, to be honest, out of a hat. I don't know why I said 10 years, but let's just say it's at some point. Yeah, at some point.
I mean, I think we're sort of waiting. Yeah, we're waiting for the common devices that we're already using to just come with attested sensors. And there are these attested sensor cameras and now microphones. There was one built last year at a hackathon. And I mean, they can put it into these devices, but it's the need has to be there, especially if there's any extra cost to the consumer. The consumer needs to want that.
Absolutely.
And I know the experiments are there, but so far it's not in everything. Although I've had this thought, what if Apple just put it in? The cell phone companies where you take so many photos from your cell phones. Why not add that little attested?
Gee, wouldn't that be a good idea?
Yeah, right?
Yeah.
But so far I don't think they're doing it. But it would change a lot, I think, if they did, at least on the real person image provenance side of things.
Very true. So eventually, maybe we'll live in that environment. Now, by the way, I should say there are some issues with C2PA. It's not that's the technology basically signs images that the camera or the Gen AI generates, but this is by itself is not enough. There's a lot more that goes into C2PA. Let me give you just one example. Maybe you have an open source model that you want to use to generate images. Well, open source models can't sign anything because they can't maintain secret keys. So what are we saying? Are we saying that open source models will not be allowed to generate images anymore? So that's not good. We have to have a solution for open source models too. But there are ways, there are kind of engineering ways to deal with this. So hopefully things will get worked out. There are always other issues with C2PA. For example, what if somebody steals the key out of the camera, right? Maybe I buy a camera, I kind of take it apart, and I'm able to get the key out.
Yeah.
And now I can issue fake C2PA attestations. We have to deal with that somehow. And so C2PA includes revocation mechanisms, and it's a large field, let's just say, but it's not as simple as just signing images. There's a lot more to it than just signing images. But here, for this conversation, let's just focus on the ZK aspect.
Okay.
So how does ZK come in? Well, ZK comes in when you want to include this in a newspaper article, right? So you have a camera that takes a picture of an event. The picture now has a signature attached to it, but the newspaper editor hardly ever uses the picture as is in the article. What they will do is they will resize the image. They'll make it smaller. Maybe they'll blur some faces.
Change the color.
Yeah, maybe they'll change the contrast. Exactly, change colors. By the way, interestingly, red eye removal is not allowed. I just found that out. It's kind of interesting.
From what? When?
The Associated Press. The Associated
Really?
Press does not allow
Oh.
red eye removal. Yeah, that's considered too much. But you can blur some faces if you want to. You can maybe crop part of the image. So there's always changes that the editors actually do, and then they put that image into the article. The problem is now the newspaper reader will see the edited image, and they can no longer verify the signature.
Yeah.
Right? Because you need the original image to verify the signature, but they don't have it. So what we did is with work with Trisha Datta and actually also with Boneh Chen. We have a paper in this upcoming Oakland. This is something that we talked about this 2 years ago. We actually even published this 2 years ago, and there's been other groups have also worked on this. But what's new is I wanted to just tell the listeners about a cute trick that may be useful to you too. So the problem in building ZK, sorry, I forgot to say what the ZK proof is proving. So what the newspaper editor will do, what the newspaper editor will do is it will remove the signature, the C2PA signature from the image, and instead it will, blur and crop and resize and all that, and then it will attach a ZK proof that says that the edited image came from a properly signed C2PA image, and the only modifications to the properly signed image is this blurring and cropping and resizing and so on. Yeah, these allowed transformations. Yeah, so now the reader, instead of verifying a signature, they'll verify the ZK proof, and they have some guarantee that the image of what the image provenance is.
Usually when I've heard this described too, it's sequential. So you wouldn't actually, you blur it, you create a proof that blur came from, that the image was coming from the previous image with a blur. And then the next step would be and you're cropping. So you do another proof, kind of proving back. Have you heard about it ever being combined?
Yeah, it's a good point. Honestly, we also do it one step at a time.
Oh, you do? Okay.
But there's no reason why you can't combine those.
Okay.
So it's just mechanically, it was easier for us to do things one step at a time, but it could also be combined. But here's the problem. So naively, the thing you have to do is you have to prove that the image transformations were done correctly, but you also have to prove that the original image was properly signed. Yeah. Now, the problem is these cameras, they will generate a SHA-256 of the image. Now, these are huge images. Yeah, they're like, the Leica camera that does C2PA, it's a 60 megapixel camera. So doing SHA-256 of a 60 megapixel image inside of a SNARK circuit, that is death. That's really quite difficult.
Okay.
Yeah, that's really quite slow. So forget the image manipulation. Just verifying that the original image was signed is actually quite difficult.
Yeah.
So that's actually what the paper is about. Yeah. So how do we get signature verification to run quickly inside of a SNARK circuit?
Interesting. What's the name of the paper?
It's called Veritas.
Okay.
Veritas image manipulation, proving image manipulation in ZK. Yeah. It's on ePrint and it will be in the upcoming Oakland conference. Cool. So maybe I'll just quickly share the core idea. So one idea is basically, let's try to improve the hash function. Let's build a hash function that's as fast as possible. And guess what? It turns out a hash function that's really good for this is a lattice-based hash function.
Whoa, back to lattice. So cool.
Back to lattices. Yeah, because lattices are just very fast. They're very fast, and they're very convenient for SNARKs to work with. So that's one way to do it. So instead of SHA-256, let's use a lattice hash, and then we can actually generate signatures. We can verify signatures inside of the SNARK at a reasonable cost. But it turns out there's even a better idea where we can take all of signature verification out of the SNARK circuits. Yeah, and this is a trick that I want your listeners to know about. So the trick works like this. So imagine what the camera does is instead of signing a hash, a SHA-256 of the image, what it will do is it will sign a polynomial commitment to the image. Yeah, so let's unpack that a little bit. So what we're going to do is we're going to treat the image as basically 60 million pixels. Yeah, we're going to treat them as coefficients of a polynomial. We're going to commit to that polynomial. The commitment is going to be very short. Yeah, and then the camera will just sign that commitment. So what the camera has to do is basically compute a polynomial commitment of the image and then sign that polynomial commitment. Okay, now you can say, well, maybe this is too hard for a camera to do. And maybe you're right. Maybe my Leica camera can't do a PCS of a large image, but certainly OpenAI can. Yeah, so the GenAI folks that need to generate C2PA images, they can definitely use a PCS of the image and then sign that PCS, the polymorphic commitment of the image. Now, why is that helpful? Well, it turns out now the ZK proof just has to prove image manipulation. It doesn't prove anything about the signature.
Oh.
The signature can be sent all the way to the client.
Wow.
Yeah, so it's a signature on a commitment. So you send the signature and the commitment to the client. Those are all succinct.
Yep.
Yeah. And it turns out magically, using Plonk, trickery, basically you can, the client verifies the signature outside of the SNARK. And it turns out the SNARK just verifies that the data that was signed actually matches whatever the SNARK circuit says. And the SNARK circuit is just about image manipulation now.
Do you get to skip the transformations, though, or do you still need the proofs of each transformation?
No, you still need to do the proofs of the transformations. What we save here is you don't need to verify the signature inside of the SNARK.
I see.
Yeah, and this is kind of a useful trick that people should know about, that if you sign a PCS of your message, then there's no need to verify the signature of your message inside of the SNARK. Yeah. Yeah, and that basically speeds things up dramatically. That's a major improvement. Yeah, so now we're actually working on provenance for videos, and the fact that we don't have to verify signatures for videos inside of a SNARK, it's a big improvement.
Changes everything.
Yeah, changes everything.
Actually, I don't know, Dan, if you've heard of this. I think there's another work on video that's come out called EVA. It's actually from one of my co-founders at ZKV, and I believe they're also tackling this realm. So
awesome! This is
we'll add that in the show
fantastic to hear, and we would love to collaborate with them. Yes,
cool.
This is great.
Nice.
Yeah, there's always. This is why this space is so much fun. There's lots of ideas floating around, and it's wonderful to collaborate with everybody.
Totally, and it's fun. It's kind of, you definitely see people go on research projects, and then they start to sometimes converge around some solution or architecture, or they've actually explored very different realms. Like, I don't think this one seems to be focused more on like IVC. I don't know that it's doing anything with the lattice stuff. So
yeah, well, of course, always lots of ideas floating around and lots of room for collaboration. This is why the space is so much fun.
Yeah. Dan, I know that we have sort of reached the end of the main topics we wanted to talk about today, but are there any like miscellaneous experiments that you would love to see people doing research on, or other threads that you're just maybe starting to explore but don't have deep work on yet?
Yeah, absolutely. In fact, we could go on and on and on. I was going to also maybe talk about accountability in cryptography, but maybe we'll leave that actually for next time. It's a lot of interesting work around that. Maybe a good way to conclude, since we're at time, is I wanted to mention that actually in the spring, I'm starting a new course. It's called Applied Zero Knowledge. Basically, it's going to be, from no knowledge of zero knowledge proofs all the way to how ZK-VMs work and folding and so on. So we'll kind of take the students through the whole journey. Should be a really fun course to teach. I'm excited. I'm looking forward to doing that. What I wanted to share is that this is going to be an applied course. So there will be programming projects. Well, the students will actually have to write code that uses or generates SNARK proofs. What I wanted to share is that our community has made SNARK proof generation so easy using these ZK-VMs that now I can't give a programming project to do it because it's too easy. Yeah,
it's too fast.
Because of ZK-VMs, it's now become so simple to generate proofs that's not an interesting project to do anymore.
So it has to be the applications.
So yes, of course, we'll do programming projects on applications, but I also want the students to understand why these proof systems work and why they're sound. And so I think what we'll do is we'll do programming projects like ZK Hack, where we take a proof system, we deliberately break it, we remove some of the checks in it, and then the students' role is to actually come up with a theorem, a statement that is incorrect, but they're able to produce a proof that the verifier will accept. So they're able to produce proofs for incorrect statements. Yeah, and this is a great way to actually learn how proof systems work, and that's exactly what I guess ZK Hack is all about.
Yeah, one of our projects. I'll just make a highlight, because actually ZK Hack Online is about to start as we're recording it, and by the time this airs, it may have just started. For anyone listening who wants to maybe get a taste for what you just said, Dan, for this sort of broken protocol and trying to figure out, how to fix it. So ZK does this puzzle hacking competition. It's the 5th time we run it. It's a multi-week event series where we do these puzzles every week. And there's like a competition to discover the bug fastest and do a write-up. So I'll add a link to that, to the latest, which is ZK 5. I'll add that in the show notes too. And if anyone's listening to this later, like after the event has already aired, we have an entire page dedicated to these types of puzzles as well. And actually, Dan, we did one last year.
We did. Yeah, that was a fun one.
In this case, do you imagine the students designing these, or would you design them and then they have to do something to them?
Yeah, probably we'll do a combination of the two. Yeah. Okay. So hopefully by the end of the quarter, we'll have a whole bunch of ZK hacks for you.
Whoa.
that you can use in future ZK hacks.
That would be so cool. Nice.
But anyhow, I thought it was kind of entertaining that now the world of ZK has progressed to the point where just giving a project to build a ZK proof is too easy.
Too easy.
And we need to do something different.
Interesting. I think we have one last thing to tease. As some of the listeners may be aware, the ZK Whiteboard Sessions Season 2 are currently airing. We have 6 of the core modules. And Dan, you have a bonus module coming later this year. And so, I just wanted to let the audience know that, I don't want to give anything away. That's my problem. I'm saying it, but we're keeping it sort of under wraps. But there is going to be a module coming later this year, sort of to wrap up the Season 2 of the ZK Whiteboard Sessions.
Yeah, I'm having a lot of fun putting it together. So hopefully it'll be a useful resource.
Nice. And actually, if anyone, I'm assuming a lot of folks who are listening know this, but you also you did the first 3 modules in the ZK Whiteboard Session Season 1. I also would add a link to this in the show notes. For me, that was my onboarding into the technical, even though it came out years after I started the show and years after I was talking to cryptographers. And it was the first time all of those words were put together in one thing. I'm like, oh, that's what they meant. Watching those videos were so helpful.
Wow, amazing.
In your course, do you think, are you still starting from that place, or would you say the space has evolved so much that you kind of how do you start teaching ZK today?
Look, the reality is that our space has expanded by so much that now you can teach multiple core courses on proof systems. There are also multiple ways of teaching proof systems. There are theory courses on proof systems. There are applied courses. There are very hands-on courses. There are multiple even ways of teaching this material. But you have to start from the same point. You have to start from zero, right? You have to explain what ZK is, what it's for. The most important thing I would say is to explain why has it become such a big topic? Why is it all of a sudden so useful? Why is there so much demand for SNARKs, whereas other cryptographic primitives you don't see as much demand for? Yeah. And the reality is just SNARKs let us do things that we can't do any other way. Yeah. And that's why they're so important. Yeah. If you want to scale Ethereum, the world of Ethereum kind of converged to L2s, and potentially SNARKs play an important role there.
Totally. Well, Dan, thank you so much for coming back on the show for this episode and giving us an update into the topics that you're researching, what you're interested in, also the course that's coming up this spring. Yeah, thanks so much for sharing all of this.
Yeah, Anna, this has been a lot of fun, and I hope you guys enjoyed it. I'm happy to do it again.
Thanks a lot. And to our listeners, thanks for listening.